x minus omega t plus pi over 2 z. I have two components to the magnetic field because the boundary condition for the magnetic field is not parallel to the surface. So I'm going to have both a parallel and a perpendicular boundary condition. Right? So I'll end up having two components to the magnetic field here. And we put that right? Yes. Okay. Then I have to do that cross product, right? And because this, well, let me think about this. I might have lost two. No, that's right. Yeah. This and this, when you perform the cross product, right, is going to give me like a sine times a sine times a cosine, plus the e to the I pi over 2. And when you do the time averaging, you're going to end up with 0. And this one will produce something. So I get energy propagation along the x direction. So when you calculate, and I'll be off by constants here. All right. I might be off by constants. That's my pointing vector. All right.
Should be 4. He said he'd be off by constants.
Yeah. 4 pi?
Yeah.
My main point here is that when you do that, you find out that one of the terms is 0 and the other term is not. And so you prove then that for these fields, the pointing vector points along the x direction. And there is no pointing vector, there is no net power flow in the z direction. You know, there's a z function here.
So we are assuming E is y hat, right?
What?
We are assuming E is y hat, or we do E?
We're assuming E is what?
Y hat is in the y hat direction.
Yes.
Then
So, can we start from those two ways, or do we need to get to those from one?
I'd like you to get to those.
What?
I'd like you to get to those. Either by logical argument from his argument, all right? So he's made his argument for p polarization, and there are just a few, and the argument goes in parallel, but there are a few switches for s polarization. So you go through the p polarization argument and then say, okay, wait a minute. I see he used these two conditions here, and you know that led to this relationship for E for the electric fields, and for the magnetic fields, and because the problem here is that you don't actually know what K is until you satisfy the electric and magnetic field boundary conditions. And then you find out that K is along the surface. And that, by the way, is enough to tell you that the pointing vector must be along the surface. But I'd like you to actually do E cross B.
So, where the actual plane that is intersecting the boundary,
Yeah.
is, what plane is that in?
That's the XY plane.
That's in the XY.
Z equals 0,
Okay.
XY plane.
Okay. And then it's traveling
And it's traveling
in the X
in
direction?
the XZ plane.
Okay, because from what
It's not traveling in the X direction.
Okay, because from what I see with that is EZIKX, but I guess.
No, that's after it passes through the surface.
Oh, okay.
So I've got an incident wave,
Right.
and then what's going to happen is that at angles, when the index of refraction becomes imaginary,
Right.
index of refraction, yeah, index of refraction becomes imaginary.
Yeah.
Or rather, the thing under the square root becomes imaginary. Index, or let me think about that for a second. The dielectric function is imaginary.
Right.
So the index of refraction has got an imaginary component.
Yeah.
Okay? That imaginary component gives rise to that.
Okay. And
You
It
find
shows in the X.
that you have these two components.
yeah.
The imaginary component is the one that ends up with if you had a propagation, if it were real, it would be into the surface.
Right.
And the real component travels along the surface.
Okay. Okay. I think I understand. I'm just the only thing is that E field transmitted. It just seems like was that originally the E to the I K X? Was that?
Yeah, the incident wave was e to the ik. Sorry, no, it wasn't.
Yeah, that's.
The incident wave was with K has got
Is a vector.
X and Y components.
Right. Okay. And since that is the case, then.
Here's X has X and Z components, doesn't it?
Oh, you're right. It's in the X and Z. K has got X and Z components.
But when you do all that, all the Z components just drop out and only have what is the X component that you're traveling across.
Yes.
Alright.
Or the way you could think about it is that the Z component of K
Pops into it.
decays.
Right. It no longer has the I in front of it.
Yeah.
Okay.
Could you redefine what you meant when you say the electric field is parallel to the plane of incidence and perpendicular to the plane of incidence?
Yes. But I'm going to use the same.
Well, because the way you explained it to me yesterday doesn't make sense now.
Okay.
Does the electric field oscillate
Yes. Hold on.
in,
Oh, good.
and the oscillation is
I don't have
parallel to
hands,
the
but I
plane?
have meter skills. Okay, so when light is propagated, all right, it can propagate with its electric field oscillating, so it's going that way, all right?
Okay,
It can propagate with its electric field this way,
okay,
or it can propagate with its electric field that way.
okay.
Now, when it's propagating like this, we just call it vertical and horizontal. Now what I'm going to do is orient it with respect to a surface, okay? And so I'm going to have a wave coming in. Let me now choose, I'm going to choose what's called in the plane of incidence, all right? A wave that's coming in, traveling this way, all right? It comes down to the surface here and goes back out again, all right? That plane that's formed by the incident vector and the reflected vector is called the plane of incidence. Okay? The plane of incidence must be perpendicular to the surface. Can't be tilted. No matter how I come in, I'm going to go out in such a direction. The plane of incidence is always perpendicular to the surface. And for electric field oscillating this way, so the electric field is traveling into the surface that way. Okay? So the wave is going that way, and the field is oscillating this way.
Yeah.
This is in the plane field in the plane of incidence. The electric field in the plane of incidence. When the electric field oscillates that way, it's perpendicular to the plane of incidence.
Okay.
In the optics books, that's called P polarization, and that's called S polarization.
Okay. And the way that you gave us S and P polarization is the same? S is perpendicular and P is parallel?
Yes.
Okay, got it. Thanks.
And I'm trying to remember, I think that Schroeder, from what I understand, uses a slightly different terminology, which is transverse electric and transverse magnetic, right? If I have my plane of incidence and my wave traveling like this, like so, okay, I believe that this is called transverse electric, and this is called transverse magnetic.
Thank you.
You tell me the reasoning is what I did was I solved.
This is that problem.
Yeah, I solved for the general, in the general where I assumed it was y.
It could be either. Oh yeah, right, that's your incident wave and your reflected wave.
This is S in total. This is just S.
Oh, that's your,
I messed with this.
yeah,
Already.
okay. No, wait, where's your B?
This is E times E cross
E cross B.
because B is E K cross not.
Yes.
So this is just the general form. So it's Y hat cross, and then I assume K has two components.